In my previous videos on the virtual number system, there were some inconsistencies and contradictions. Thanks to everyone who pointed them out in the comments and Discord communities. Now, this is the final revised version, where everything is consistent and fully developed. The system works smoothly, and I'll walk you through all the key concepts step by step. In traditional mathematics, when we try to take the square root of -1, we introduce imaginary numbers and define a special symbol I, such that I squared equals -1. This gives us the system of complex numbers, where any number is written as a plus bi. But what if, instead of defining an imaginary unit, we take a logarithmic approach? This leads us to the virtual number system, where we define j is equal to the natural logarithm of -1. This changes how we think about imaginary numbers, trigonometry, and even geometric transformations. We will derive everything step by step, from square roots, exponentials, and trigonometric functions to the roots of unity and the geometric differences between the complex and virtual planes. Let's get started. 1. Defining the virtual number system. We define the fundamental unit of the virtual number system as j equals the natural logarithm of -1. From exponentiation, we know that e raised to the power of j is equal to -1. This is our core definition in the virtual system, just like saying I squared equals -1 in the complex system. Finding the square root of -1 in the virtual system. We now find the square root of -1 in the virtual system by solving x squared equals -1. Taking the natural logarithm on both sides gives the natural logarithm of x squared is equal to the natural logarithm of -1. Using the logarithm rule that says the logarithm of a number raised to a power is that power times the logarithm, we get 2 times the natural logarithm of x is equal to j. Dividing both sides by 2, the natural logarithm of x is equal to j over 2. Now, exponentiating both sides gives x is equal to e raised to the power of j over 2. Thus, in VNS, the square root of -1 is e raised to the power of j over 2. This is our equivalent of I in the complex system. 2. The virtual Euler formula. In the complex number system, Euler's famous formula states e raised to the power of I times x is equal to cosine of x plus I times sine of x. We now derive the equivalent for the virtual number system. Expanding e to the x in the virtual system. Let's substitute x equals theta times e raised to the power of j over 2 into the standard Taylor series for exponentials. E raised to the power of x is equal to the sum from n equals 0 to infinity of x to the power of n divided by n factorial. Now, substituting x equals theta's e raised to the power of j over 2, we get e raised to the power of theta times e raised to the power of j over 2 is equal to the sum from n equals 0 to infinity of theta times e raised to the power of j over 2, all raised to the power of n, divided by n factorial. Rewriting the exponent using exponentiation rules, e raised to the power of n times j over 2 is equal to -1 raised to the power of n over 2. Thus, for even powers, we get e raised to the power of 2k times j over 2 is equal to -1 raised to the power of k. For odd powers, we get e raised to the power of 2k plus 1 times j over 2 is equal to e raised to the power of j over 2 times -1 raised to the power of k. Splitting the series into even and odd terms, we get e raised to the power of theta times e raised to the power of j over 2 is equal to the sum from k equals 0 to infinity of -1 raised to the power of k times theta raised to the power of 2k divided by 2k factorial plus e raised to the power of j over 2 times the sum from k equals 0 to infinity of -1 raised to the power of k times theta raised to the power of 2k plus 1 divided by 2k plus 1 factorial. Recognizing these as the cosine and sine series, we obtain e raised to the power of theta times e raised to the power of j over 2 is equal to cosine of theta plus e raised to the power of j over 2 times sine of theta. This is the virtual Euler formula, the virtual number system's version of Euler's identity. Finding the inverse and modulus in VNS for a virtual number v equals a plus bj, we find its inverse by solving 1 over v is equal to 1 divided by a plus bj. Multiplying both the numerator and denominator by the conjugate a minus bj, we get a minus bj divided by a squared minus b squared times j squared. Since in our system j squared is equal to negative pi squared, we substitute a squared minus b squared times negative pi squared, which simplifies to a squared plus b squared times pi squared. Thus, the inverse of v is a divided by a squared plus b squared times pi squared minus bj divided by a squared plus b squared times pi squared. Modulus in the virtual system. The modulus of v equals a plus bj is defined as the square root of a squared plus b squared times pi squared. Notice how the pi squared factor appears, making it different from the complex modulus. Finding the roots of unity in virtual numbers. In complex numbers, the cube roots of unity satisfy z cubed equals 1. The solutions are 1, e raised to the power of 2 pi I over 3, and e raised to the power of negative 2 pi I over 3. In VNS, we solve z cubed equals 1. Taking the natural logarithm of both sides, 3 times the natural logarithm of z equals 0. Dividing by 3, the natural logarithm of z is equal to 0, j over 3, or negative j over 3. Exponentiating, we get z equals e raised to the power of 0, e raised to the power of j over 3, and e raised to the power of negative j over 3. So the roots of unity in virtual numbers are 1 e raised to the power of j over 3 and e raised to the power of negative j over 3. Unlike the complex case, these do not lie on a unit circle, revealing a new geometry. Why the virtual number system is useful. So what makes the virtual number system unique? At first, it may seem similar to complex numbers, but our deeper exploration reveals something fascinating. In the complex plane, multiplication results in perfect circular rotations. Every transformation preserves angles, making it ideal for wave mechanics, signal processing, and quantum physics. But in the virtual plane, multiplication follows an entirely different geometric structure. Instead of circular motion, numbers undergo a skewed transformation due to the scaling factor. The virtual plane does not behave like a unit circle. Instead, it distorts in a way that changes distances and angles uniquely. Traditional complex numbers work perfectly for oscillatory and rotational systems. But what if we need a system where rotations are naturally distorted, stretched, or compressed? Mathematics evolves when we challenge existing structures. The virtual number system doesn't replace complex numbers. It offers a new way of looking at transformations, unlocking possibilities yet to be explored. If you found this intriguing, let me know in the comments. Where do you think virtual numbers could be applied? Don't forget to like, subscribe, and stay tuned for the next deep dive into mathematical structures.